the title of our presentation is Interaction between tension and cyclic torsion on non-ferrous materials. The co-authors are by name Tadeusz Łagoda, and next Joanna Małecka, she presented this second part. Karolina Głowacka, you are from Opole University of Technology, and Huang from Tsinghua University from Beijing in China. Sorry, I put one time. I don't understand.
Not working properly?
Yes, I put one.
And it goes menu. Yeah.
Film. Okay, maybe I will put.
No, can I click when you signal? You want?
Okay.
Alright.
Okay, it will be a pointer.
No, but
The same?
yeah, the same. This one?
Yes. We have two non-ferrous materials, aluminium alloy and brass. It's very important. The shear, maximum shear for brass 339 and for aluminium 242. So next, I go to her. It is our statement is typical statement used in our university. It's very small statement. It's very cheap also. Stand on the last slide. You may see the stand. It is stand. It is made at our university. It is stand for bending and torsion. Every combination we use in our experiment only torsion. And we know that for brass, for numbers of cycles 100, thousands, you have moment of torsion. It's generally in this time it should be fiber. And for aluminium alloy, we take 50,000 cycles, it will have moment. And we did several experiments. At first, we have fatigue test of the 20, 40 and 60% of number of sites. This is theoretically should be. And next, we have calculated the maximum stress. And other, we have pre-damage statement. Please. And the static test was used in this instrument equipment. This next. Okay, so we may see at first we did fatigue of shear stress of torsion. We decided stop, and next we did static test up to fracture. Next, sorry, this problem with presentation. No. We on the right hand, I should. No. Earlier. Okay. This is okay. And next, we did some press stresses more than plastic. And next, we did experimental of fatigue torsion up to fiber. This next will be. Yes, here it is. We see that at first we have here this plastic stress, and next we did some fatigue element. We see that we have small fatigue, only 20,000 of size. Normally it should be 100. We have small plastic stress. For more fatigue experimental, the plastic stress for this material is very similar. Next, it will be okay. And here, yes, it is aluminium. So we see that when we have some area fatigue, the plastic stress always is less. Especially, it's very interesting that for small fatigue, we have decreasing of plastic stress of this material. And here is opposite. At first we have plastic and we have press stresses, several press stresses, and after them we did experimental or fatigue. We see it should be 100. It depends of press stresses. It is some tendency you see. Of course, it wasn't 1 point. In every time it was 2 or 3 spacemen. It is mean value. Is and here we have for aluminium alloy, we see that press stresses increasing the number of sites. And next, it was analysis of fracture. It was made by Joanna Małecka.
Good afternoon. My name is Joanna Małecka, and I want to show the second part of our presentation, the analysis of the fracture. We can back?
Okay.
Okay. So the fracture images, we can observe it on the desk scanning electron microscopy operating at 20 kilovolt, and the secondary electron detection was used. So now we can see the fracture for the brass specimen obtained after the first take of test, depending on the number of cycles. The next are fracture for aluminum. Okay, so for the brass, observation of the brass and aluminium confirms the general known mechanics of fatigue failure occurring during cyclic torsion at a large number of cycles, and the fracture display the fatigue imitation, the fatigue zone, and the residual zone which occurs most of the surface. The fatigue imitation for brass is characterized by a rough surface and an irregular fault propagating in a random direction. This picture shows the fatigue zone fillet with micro areas of strain with different orientation, and the next picture taken at the magnification of more than 12,000 shows the residual zone. In the case of aluminium, the fatigue imitation is easy to locate, and the fatigue zone is clearly marked and distinguishable from the residual zone. And the fatigue imitation is accompanied by deep and numerous cracks, which are also clearly visible in the fatigue zone. And the next picture shows the area in the residual zone. Now we can see the fracture for the brass obtained after the second take of test, and the next are fracture for aluminium. And for the brass, we can see a small circular area centered around the axis of the tangential stress distribution, which is shown at higher magnification in this picture. And the next are image for the residual zone. The observation, the fracture surface of aluminium is it's clearly different from the brass samples. Performant observation allowed the identification of the potential fatigue imitation where the mine crack had formed. However, observation all the zone it not reveal the microscopic structure. And conclusion. Sorry. Okay. So for the first change in the yield point for brass, the small degree of damage we obtained the slight decrease about 5%. Average degree of damage it's practically no change. For aluminium, the small degree of damage we obtained more than 10% decrease. Damage degree we can obtain slight increase of the yield point, and in the the damage degree 0.6 we obtain degree about 5% from the initial yield point. And for the both materials, a small degree of damage decrease of the yield point. And the second, so the influence of the specimen pre-stretching above the yield point on fatigue life. For brass, 10% above the yield point, it's no significant change. For the 459 megapascal, we obtain increase in fatigue life about 50%. For 165 megapascal, its fatigue life decreases. For the 490 megapascals, 15% decrease in fatigue life. Analysis of the structure. So for the first step, the type of test, the areas of the plastic micro deformation appear and fatigue micro cracks nucleate, which then merge into the mine cracks, forming fatigue imitation, and as a result, cracks propagation, a fatigue zone is created in the material, while the result of rapid failure at the weakened material is a residual zone. And generally, observation of the fracture for both material is plastic and ductile, and the voids is indicated that they were very weak areas of the cross section, and therefore a convenient place for a development of the residual zone. And for the second type of test, the fatigue micro cracks nucleate, which merge into the major cracks, and this result in the development plastic fracture. Thank you for your attention.
It's a problem with computer every time. Now it's time for some question. Please.
So in your fracture surface, that's sort of like a spiral kind of fracture surface. Is that? I'm not so familiar with torsional tests, but is that like a common fracture surface? The one that sort of like was showing a beautiful spiral.
For aluminium.
Yeah.
This fracture, yes. This.
Yeah, that one. Yeah.
This. Mm-hmm.
Is that common that you really have this sort of like a spiraling internally with a torsional fatigue test?
I observed this fracture only for this sample, the aluminium. Sorry, yes, and this.
Yeah, but the other one, that more on the left, is more like it seems more like a cup and cone one. But the top right one seems really like it's a crack that starts from the surface and then runs over the surface and gradually starts propagating inwards. Did other people see it in the literature? I find it fascinating actually.
I guess I don't know, but I observe only this that the value of yield increase, the area is more visible.
Yeah, okay,
But
understand. Okay, thanks.
Okay, thank you. Other question? If no, thank you for question. Thank you for the
Thank you.
presentation.